So this is the binary star problem. And I'm setting this up, and it doesn't use a lot of really difficult physics, but I'm setting it up to use it for more complicated physics, in particular the one-dimensional equivalent one-body problem. So this is really a two-body problem, but if you have it in circular motion, it's not so bad. So what I want to do is show you how to calculate the velocity, the initial velocity, so that it's in a circular orbit, and then model it in Python. So let's do it. Let me turn this off. Turn that off and get over here. Move my mic. Okay, so we have two stars here, mass 1 and mass 2, and they're separated by some distance. Now there's a couple things that I want. I want A, the center of mass at the vector 0, 0, 0. I want the center mass at the origin. And that doesn't have to be the case. I just want it to be that case to make things easier. Second, I want the total momentum to be 0. Or you could say that as the momentum of the center of mass to be 0. And that way the thing doesn't move. That thing's bothering me. And then finally, I want circular orbits. And you may say, well, look, I have these two objects interacting, and that's kind of complicated. They're not going to move in circles, but they can move in circle. Okay, and that's what I'm going to show you how to do. So let's start with the center of mass. I'm going to say that the star 1 has a mass m1, star 2 has a mass m2. The distance between them is some set distance that they're going to orbit at. So let's first find this. So I'm going to say this is R1, the vector location of star 1. This is R2, the vector location of R2, and I want that to be, I want the center of mass to be at the origin also. So we can define the center of mass. I can call this capital R. R, center of mass, is defined as mass 1 times its vector location plus mass 2 times, well, that's 1, times its vector location divided by the total mass, m1 plus m2. This is the definition of center of mass. Now, let's just go ahead and set this equal to 0. All right, I want it to be at the origin. I want the center of mass to be right there. If that's the case, I can multiply both sides of this equation by the scalar m1 plus m2. That's pretty easy. So then I get m1 r1 equals negative m2 r2. That has to be true for the center of mass to be at the origin with just 2 points. Okay, so let's set this on the x-axis. Let's call that x. Let's call that y, just to make things easier. We can get some values here. So I can put this at, this is going to be x1, and this is going to be x2. So now I get m1 x1 equals negative m2 x2. But I also know that x1 plus x2, no, I don't know that. So if I look at the vector location from here to there, r, I know that it's going to be the final position r2 minus initial position of r1. So I know this is true. R equals r2 minus r1. It's the displacement vector from star 1 to star 2. So that means that in the x components of this, if everything's in the x direction, I could say, let's just call this the magnitude of r, because it's in the x direction. It's going to be x2 minus x1. Now, x1 should have a negative value, right? So that means that whatever this distance is plus this distance would be r. So that is indeed true. So if I use this with this, I can solve this for, let's solve this for x2. So x2 equals r plus x1. And so I'm just calling r the magnitude of the distance between those two. And I dropped off this magnitude stuff. Now if I plug that in over here, I get m1 x1 equals negative m2 r minus m2 x1. So if I add this term to both sides, I get x1 times m1 plus m2 equals negative m2r. And from that, I can solve, I'll put it right up here, x1 is going to be negative m2r over m1 plus m2. So that's, if I know the masses, and I know the distance between them, I know where to put mass 1. And then I can find out where to put mass 2 by just adding that to r. So x2 equals r, which is a known value, I pick that, plus, well, it's actually negative m2 r over m1 plus m2, which is this. And you can actually factor out the r if you want to. So let's say x2 equals r times 1 minus m2 over m1, and you can't see that, plus m2. My camera is a little zoomed out. Okay, so those are my locations. So now I've gotten this part. The center mass is at 0. Let's do the total momentum is 0. Okay, so going back to my binary stars. And that's R1. And that's R2. So if I say R center of mass equals M1 R1 plus M2 R2. My camera looks a little washed out right there. I need to work on my lighting. Over M1 plus M2. So this is the total mass. So let's just say M1 plus M2 equals M. So then if I multiply both sides by M, I get M, R center of mass, equals M1 R plus M2 R2, R1. Now, there's two things I could do now. I could either take the derivative of both sides, but if you don't want to do that, you could say I'm going to divide by some time interval, delta t. I'm going to say take the derivative. Let's take the derivative of this, and the derivative of the position is the velocity. So I get m total v center of mass vector equals m1 v1 plus m2 v2. Now, we define momentum as mass times velocity. So this is the momentum of the center of mass equals the momentum of 1 plus the momentum of 2. If I want that to be equal to the 0 vector, right, these are vectors, then p1 equals negative p2. So if I pick some velocity for mass 1, it doesn't really matter what. Let's say it's like that. That's actually too big. Because has a bigger mass. This is 1 and this 2. Then I know this has to have a momentum that has the same but opposite magnitude. It'd actually be a bigger vector. So it'd be v2. It'd have to be in the exact opposite direction where m times this is equal to m times that. So once I find the velocity for one star, I can find the velocity for the other one using this. Okay, so that's the second part. Now for the circular orbits. I'm going to redraw my binary star again. Let's draw it a little bit smaller. And there's my center of mass. Okay, so let's just call this a green one. And let's call this the red one. And so if you have these in a stable orbit, it turns out that this will orbit the center of mass. Now I know you're thinking, that doesn't seem legit, but I'm going to show you it's legit. It's actually too legit to quit. My green thing doesn't look, let's just draw it like that. And then the red one will also orbit the center of mass. So they'll both have circular orbits like that. And again, you may say, no, that's not true. Okay, let's do it. Let's set it up and then we'll model it and I'll show you that it's true. So what do we know about this mass 1? We know that there is a force on it. There's a gravitational force pulling that way. The magnitude of that force, Fg, is going to be g mass 1, mass 2 over r squared. That's the universal gravitational force, where g is 6.67, that's a 6, times 10 to the negative 11th, newtons meters squared per kilogram squared. And what do forces do? Well, that's the only force. In general, F net vector equals mass times acceleration. But if there's only one force, that force has to be in the same direction as acceleration. So and let's just call that the x direction at this instant. So F net x is going to be equal to g m1 m2 over r squared, right? Because this is an attractive force with this other star, so it has to be towards that other star. Now, if this is moving with some velocity v1 that way, a little bit later, it's over here if it's in a circular orbit with the same magnitude of velocity but in a different direction. Since acceleration is defined as the change in velocity divided by the change in time, or the derivative, my handwriting's terrible, then this, even though it's moving at a constant speed, is indeed accelerating. And it turns out the magnitude of this acceleration, I'll put a link down below, see there's an arrow, is equal to v squared over r1. And I didn't say r, in general it's v squared over r, but it's r1 because it's the radius of the circle it moves in. And you'll notice that this is r, the distance between the two planets, and that goes right here because the gravitational force depends on the distance of those two. The acceleration depends on the distance between the size of the circle, which is r1, not r. Okay, so now I can put this all together. This is going to be equal to the mass of star 1, m1, times v1 squared over r1. See that? Okay. Now, I want to solve for what velocity is going to make this work. I already know what r1 is, so I can just cancel these two masses, solve for v1. I get v1 is equal to the square root of g m2 r1 over r squared. And again, that's the distance, the radius of the circle. That's the distance between the two planets. But I actually already know, where'd I put it? I already know a value. I know that the magnitude of r1 from before is equal to negative m2, that's actually, x1. So r1, the magnitude, is equal to m2 r over the total mass. So if I put that in up here, I get v1 equals the square root of g m2, and then I need to multiply by m2 again, squared, and then I'm going to have r divided by r, so I get r, and then I have m. Wait, I messed up. m2 over m. Yeah, I'm pretty sure that's right. I feel like that's not right. I feel like I made a mistake. I have just m. What did I mess up here? x1. I have it in another calculation. I'm just looking at my notes. I have g times m2 over r, not m2 over. I mean, it has the right units, but. Oh, I know what I did. Okay, I think this is right. Yeah, this is right. I'm pretty sure this is right. So then once I calculate the velocity, and this would have to be moving perpendicular to the radius, so this would be starting off in the y direction, and then this would have a velocity v2 would be equal to negative, in the negative y direction, then it would be m1 v1 divided by m2, right? Because this is setting up the momentums to be equal and opposite. So there's my velocity from star 2, and they will orbit. Now let me just go ahead and say why they orbit. Imagine this is a stable circular orbit, so they stay the same distance apart. They're going to have to move with the same angular velocity. They'll have different speeds, but the same angular velocity. If they didn't, then this line, imagine this one gets down here, and that one gets right. It's further, it's up there. Then this does not pass. The center mass had to change, right? But I already said the center mass was constant and at the origin. And so the only way for that to happen would be these to have the same angular velocity and always be opposite of each other. Okay, let's switch over to Python and let's model this thing. I'm going to need to do, I'm going to have to pick some values. And let me go over the quickly how you do this numerical model if you haven't seen it before. A numerical model solves a problem by breaking into small time pieces. So here's my 2 planets. Let's say this has a momentum P1, and this has momentum P2, and this is the vector r. I can calculate, let's do P2 over here. I can say r equals r2 minus r1. I need to do that. And then I can calculate the gravitational force as this, Fg vector negative g m1 m2 over the magnitude of r squared times the unit vector r hat. So what that does is I need this as an actual force vector because everything's going to be changing directions. I have to have a force vector. This vector r is a vector and I can't square it. So I have to take the magnitude first. And if I did that, I'd get a scalar value. This r hat says take the direction of that vector, r hat, and then multiply by negative sign, so I get the force going this way. And then the force on this one's the exact same thing, but the opposite value, because forces come in pairs. After that, I can use the momentum principle. This says F net is delta P over delta T. And if I assume a short time interval, I can assume the force is constant over this time interval, which it's totally not. But I can assume that. If that's the case, this is going to be P, let's call it as P final minus P initial over delta T. And I can solve for P final at the end of the time interval. It's P initial at the beginning of the time interval plus F net, which is only Fg, times delta T. So I can take the momentum at the beginning of the time interval and find the final momentum by assuming this is constant, which it's not. And then I can do the same thing for position. R final equals R initial plus P final over m, which is the velocity, times delta T. And that comes from V average is delta R over delta T. So then so here's what I'm going to do. I'm going to calculate the distance between them, calculate the force, use that to update the momentum, use that to update the position, and then update time. T final equals T initial plus delta T. And then go back over and do it all again. And just keep doing this. And during those time intervals, I can assume that the forces are constant. I can assume that the momentum is even constant to calculate the position. And if my time interval is small enough, it works. Okay, so let's do this. I'm going to switch over to Python. I need to pick some values for some stuff. I'm going to go fast because I'm excited. So just bear with me. Let me move my mic. Switch over here. Okay, so I'm using, this is GlowScript vPython, and this is actually Trinket. So Trinket is just a different implementation of that. I'm going to go down here to, if Trinket.io, if you haven't been there, it's awesome. They have a whole bunch of cool things. You can see they have Python, regular Python, GlowScript, Java, R, Pygame, music. But we're going to go down here to GlowScript. That is Python with the visual stuff built in. And now you could do it as dragging these blocks around, but it'll drive you crazy. So I'm going to do this. I'm going to make this bigger because people can see that. I think it should be big enough. Okay, so I'm going to go ahead and enter my constants first. So let's say G equals 6.67 times 10 to the negative 11th. I need mass 1. Mass 1 is going to be equal to, I'm picking on the order of the mass of a star. Mass 2, let's pick 0.7 E30, just for fun. And then the distance between them, I'm going to call this R dist. It's going to be equal to, let's say, 2 times 10 to the 10th. I just picked a value again. So the first thing I'm going to do is make my 2 stars. So star 1 is an object of a sphere. I'm going to go ahead and run this. In case you haven't seen Python before, let's save it. Binary star stuff orbit. Save. I'm going to run this. And so by putting the name sphere in here, vPython makes this 3-dimensional sphere. I can rotate around and zoom in and out. So it does all that heavy 3D work for me. but I can make it even better. So let's make this, let's give it a position. Yeah, let's go ahead and do that. I guess I should calculate that. So let's say R1, and I'm getting my notes over here. Remember, we calculated the location of R1. I wrote it as X. It's going to be equal to, let's just calculate the magnitude. M2 times R dist divided by M1 plus M2. I should call that M. It'll be easier. M equals, Python is case sensitive, M1 plus M2. So now when I go to find the position of star 1, I'm going to say it's at the vector location negative R1, 0, 0. I need to give it a size, radius equals, what did I use before? 10 to the 9th, E1, E9. And you can't make that a realistic size or you won't be able to see it. And then I want to give it a color yellow. I want to give it a trail. Make trail equals true. Okay, nothing's going to happen, but let's go ahead and run this and see if, something. Okay, so there's my, you'll notice I have a smaller star because it got shifted off the origin and it's yellow. Let's do star 2 is sphere, position, I didn't need to calculate R2. R2 equals, that's right. R2 is equal to R distance, I'm just copying my notes, times 1 minus M2 divided by M. So this is going to be equal to vector R2, 0, 0. Let's make this one smaller. Radius equals, say, 0.6 times 10 to the 9th. And, for colors, I can make this one cyan color because it shows up well in the black background. And then make trail. The make trail, as it moves, it leaves a trail behind it. And that's going to be cool. There it is. Okay, now just for fun, let's do this. rcom equals, let me do this. I'm going to be a good Python programmer. Star1.m equals M1. Star2.m equals M2. That's setting that parameter. Instead of having to use M1 and M2, I can always just refer to star1 and star2. So now rcom is the center of mass. It's going to be equal to star1.m times the vector location of star1 is star.pos. So I don't have to say R1 and all as a vector. Star1.pos is the vector location. I'm using that actual 3D object as my variable. Plus star2.m times star2.pos. All of that divided by m. And now I'm going to put an object there. So let's call it com, sphere, position equals vector. No, just rcom is a vector. I did that as a vector. And then the radius, it should be smaller. So let's say 0.1 E9. And then the color will just leave as white. And this is just a check. Yeah, see, there it is right there. Okay, there's my center mass. That's in the origin. Things are working. Things are happening, people. Okay, now I need to enter my velocity, v1. So I'm going to use my calculation up here, v initial, v1 initial. And I'm just going to type in what I had before. So it's equal to the square root of g times star2.m. Wait, yeah, squared in Python is star, divided by r distance, the magnitude of r, doesn't really matter, times m. Now I can say star1.p equals star1.m times the vector v1 init 0, 0. So it's going to be moving in the positive y direction initially. And then for star2.p equals negative star1.p. Right? I want them to have equal and opposite momentum so the center mass is 0. Now I need to do time. Scroll this. So t equals 0. dt. how small is a time step need to be a small time step? Well, if I was throwing a ball in my room, a time step of a hundredth of a second would be appropriate. But for these planets, in a hundredth of a second, they don't even really move, even though they're moving really fast. So that's not going to be enough. I'm just going to pick, and actually I already did this, so I'm going to pick. I'm going to say 100 seconds. That's fine, and I'll show you that it's wrong. Now I'm going to do a loop while t less than 1 e5. I'm just guessing here, right? I can change these. So this is a loop in Python. It says everything indented below this is going to be part of the loop. And so the first thing I'm going to do is to calculate the position, the vector from one star to the other. R equals star2.pos minus star1.pos. And I have to do that in the loop because as these things move, that changes. Yes, it's hopefully the same distance, but the vector changes. And since the force depends on the vector, I do need to recalculate that. Now I can calculate F2. This is the gravitational force on 2. I don't know why I did it this way. It's going to be negative g times star1.m times star2.m times norm r. Norm r is a built-in function in Python that returns the unit vector in the direction of r. So I don't have to do that manually. And then I need to take the magnitude of r, also built-in function, squared. Okay, now we're ready to update the momentum. So I will say, let's do star1 dot, you gotta spell it right, dot p equals star1 dot p minus F2 times dt. So here I'm using a minus because that's the force on star 2. Star 1 is the opposite of that. So that's why I have a minus sign in there. This is star 1 dot p equals star 1 dot p because that's not an algebraic equal sign. This says take the value of the momentum, add that thing in there, and then make that the new value of the momentum. So that's a way of updating the momentum. Star 2 dot p equals star 2 dot p plus F2 times dt. Right, because that was calculated for that. Now I need to update the positions. Star 1.pos. This will actually move the stars. Star 1.pos equals star 1.pos plus the velocity, which is star 1.p times dt divided by star 1.m. I'm going to give you the code. Don't type it this fast. Star 2.pos equals star 2.pos plus star 2.p times dt divided by star 1.m. I think I need to update time. I think that's all. T equals t plus dt. Otherwise, this loop will never end. Okay, let's save it. Do you think there's a syntax error somewhere? What do you think? Okay. That's not right. Aha! I know what I did wrong. Do you know what I did wrong? Right here. I gave it an initial y velocity, x velocity, instead of an initial y velocity. I was dumb. Okay, so they're moving. Is that right? I don't know. Let's do it for a longer period of... Oh, there's another thing I put in here. Rate 100. So rate tells Python how many calculations, how many loops to do every second. You notice it happened really fast. I want it to run out and play out in some slower amount of time. So here you can see them moving. Let's actually speed that up. That's let's do that for let's make a longer time step, and then make this longer and see if I run it. There we go. Check it out. I need to add one thing. And that is I need to update the position of the center mass. Let's make sure the center mass stays stationary. But here you notice circular orbits, like I said. Okay. So let's update the position. Let's recalculate the center mass right here. And put So put that there, recalculate it because everything moved, and then say com.pos equals rcom. And let's see if it moves. And it's not going to move because I did it right. Okay, look right there. Not moving. Winning. Okay, wait. Not winning. We're going to win in just a second. Watch this. What if I change this and make it go faster than circular orbit? Let's say 1.1 times that. Too fast for a circular orbit. The program still works. The center of mass is still there. They're just not moving in circular orbits. But it's still a calculation. Still momentum's conserved. The center of mass is still the same. It's just not a stable orbit. Well, it's still stable, but it's not a circular orbit. And so you can play around with this cool stuff. The code here still works, right? The numerical calculation doesn't care whether you make it a circular orbit or not. It still does. It's still circular, actually. Let's make it not circular. Let's say minus 0.2 times v init in the x direction. Oops. Can't find variable v1 init. Okay, so there you go. It's still two-body problem. And really, I'm setting all this up so that we can do an equivalent one-dimensional, one-body problem using some more complicated physics. But we need some examples to work on, and this is the binary star system. Okay, so the code's below. I'll put some things down below about centripetal acceleration. I told you I would. And I will stop here and talk to you guys later.